Hello. So in this video, I will show you how you can use the Fracture Surface Analysis Toolbox in Matlab called FSAT to analyze the roughness properties of two profiles that form a vertical cut through fracture. I recommend to watch the video where I show how you can use FSAT to calculate the roughness of a single height profile first, because here I will only show you what is different compared to this single cut, this single height profile. Again, my starting point is the generate metadata.m file, where everything is explained, how you provide the metadata for FSAT so that FSAT can operate and analyze your dataset. In the case we're looking at today, the example given here is the sample 3, and I just copy-pasted the important information out to an extra file to have more streamlined for you what you need. So again, I will have a fresh start, remove everything that is on my workspace. I need to provide the file of my metadata, how it's called. Here I decided to call the file metadata.cut. In this file, at the end, I will store what I define here as an example. So very similar to the single height profile, I need to specify the case. For two height profiles, it is the letter C. This is all explained in the manual, in the publication, as well as in the generate metadata.m file. Again, I want to have a figure output. I want to have it in PNG format. I provide a name. And now there's a difference. I have to provide the data to top and bottom files. Make sure that you know which one is the top, which one is the bottom, right? Again, I give a pass to the results folder. And now everything, until here, everything is similar to what is provided for a single height profile. So I don't want to really go through this here in detail. What is new is that I can provide an aperture value. So this is the mechanical aperture, so the main mechanical aperture. So FSAT will compress or bring both surfaces as close to each other until this mean aperture is achieved, or something close to this. Can't match it exactly, but very close to this. So the only thing I have to do now is to run this metadata file. You will see it generates me a metadata.cut file in my FSAT folder. Now I need to provide this file name to the analyze sample script, right? So provide this here. This is everything I need to do, and now I can run this analysis. All right, again, you see that FSAT is having some kind of output here. It generates my figures because it want asked it to do. It provides me with some information here. There's a metadata checker. It identifies the sample correctly as a 2D fracture, and all metadata is provided, so it's happy with that. And you see the analysis is going on. The fractures look different a bit. Provides me all the figures you already have known from the 1D example, and it should come to an end pretty soon. And here we go. So if you look at the generated output, so we have the older, the folded test results. In the folder test results, it generated a folder fracture 2D because that's what's specified in the metadata. And now you see that they're different hierarchies. So we have bottom and top separately, and then we have some common analysis. Whatever you will find here in the top and bottom folders is exactly what you would find if you would have analyzed both top and bottom height profiles separately. So I won't go through this one again because I did this as I explained to you how to analyze a single height profile. So more interesting for us is what now comes from the joint analysis of those ones, and this is especially to do with the aperture. So for example, we can take a look at the aperture distribution, and we see now how in one coordinate system the top and the bottom surface are aligned to each other, You see there are different touching points. You can read in the publication how the algorithm handles those kind of touching points. All right, and you can see on top of that in red the apertures. So very obviously here in the mean region, you have a very high aperture and very small aperture values towards the ends of both fractures. You can also look at an histogram of those aperture distribution. You see, well, okay, there are a lot of points which are in contact, right? And then you see, well, okay, that is almost homogeneous distributed until 1.5 millimeters aperture distribution, and there's a very few points with very high aperture, with up to 3 millimeters. Again, you get CSV files, which provide you with all the information, but we would rather look at the mat files because they provide everything that we have in the CSV files as well. Again, I can look in the results folder for the aperture. It gives the mean, the min, the max aperture, the standard deviation of the aperture, and the contact area provided in the units squared I provide in the raw data. So in our case, that was millimeters, so this is millimeters squared. Okay. I can also look at the sample, which gives me just simple metadata, and we get the aperture as a table, and we get the XQ, so the corresponding X values of this aperture. We can also take a look at the workspace map file, which provides with a similar result as we know for the single height profile, but now for both surfaces joined. So we can look at the differences between the height profiles. So for every parameter, we provide you with the top and bottom, so for both surfaces, the difference between both surfaces and the mean value if we have both of those. Right. So again, these are the same parameters that we always calculate with FSAT. Right, and we can, for example, look at the JRC value. So you see those two are very different, 9 and 12. That's quite a lot in the JRC world. But you will see, okay, that the difference is -3, so you might not want to consider a mean value here, right? But maybe those two are very equal, and you decide, okay, I can describe both profiles with the common value, and then you just get the mean value here. Right. Again, we output mean, min, max, and STD values. For 1D profile, all those three are common, are the same value. The JRC is 0, and the standard deviation is 0. But for the 2D profile, this will make more sense, as we'll discuss later. Right. So this provides you everything you need, and the structure also just provides you again with the metadata so that you always know what you used as an input. So you see, this is very simple. It's very similar to how to handle 1D height profile from the output. You just get additional information about the aperture, and you get a comparison of both height profiles. Thank you very much for your interest. I hope this video was helpful, and I hope you enjoy using FSAT.